Hi, it's Charlie Zeiss with Stargate Pyramids and the Pyramid Science Foundation. Today's video marks the first research video I've really had the time to do in probably almost 6 months, just due to the overwhelming demand for Stargate Pyramids that's occurred over the last several months. And I'm grateful for that, but I'm also grateful that as things have slowed down a little bit, I've been able to take back up some of the research projects that I've been anxious to get back to for quite some time. And the major focus of my research these days is focused on trying to develop a model of the creative process. And to put this into context for those of you new to my research, I'm going to try to explain what the creative process means for those of you who are new. And I do this via example. When I was a young child, I grew up in the Christian church, the Lutheran church, and I would go to church every Sunday. And I'd be told to pray to God, and if God answered my prayers, to be grateful. And of course, I was. But when I would ask the question of my Sunday school teacher, well, how did God do that? I wouldn't get an answer that really made sense to me. It would be something like, well, that's a miracle and that's beyond our comprehension. But as I grew up and in adulthood began going to metaphysical church, I began to understand and awaken to the fact that our thoughts do create our experience. And as a result, I then had to question once again, isn't there a process through which, there must be a process through which that pure thought is translated into my physical experience. So all of a sudden I knew that there had to be a harmonious universe that responded to my intention and to my thinking by taking that and creating it in my physical experience. So I've been on a search for quite some time now to try to develop a model that can do that. And that's really the outgrowth of why I'm interested in and excited about bringing this information to you today. The title are the Generalized Fibonacci Formulas, the model for universal Phi scaling. I know that's going to sound a little intimidating to people at first, but I want you to know that this is not going to be a video only for math majors. We're going to take it and present it in such a way that everyone can understand this. So when we do get to some of the mathematics sections, just hold on, it won't last too long, and you'll be able to follow along shortly thereafter, because I'm going to demonstrate these not just with mathematical formulas, but with real life applications and examples. So let's get started. What I want to do to begin with is to just give you some background and introduce this topic before we get started in earnest. Naseem Haramein, Dan Winter, Marshall Lefferts, and other significant researchers in this field have all generated substantial evidence that Phi scaling is found in all facets of the universe. And it's found from the macro or galactic down to the subatomic. And to date, there hasn't been a mathematical model that at least I have been able to find that depicts exactly how this universal Phi scaling is accomplished in nature. So that's the purpose of this discussion today, because I know that my pyramids are Phi-based in geometry, and therefore I'm very, very interested in finding how the pyramid geometry will interrelate with this scaling methodology that's used by nature. And one explanation as to why this universality of Phi scaling has not resulted in an adequate model to describe it is the fact that, unfortunately, there's a false belief held by many of the authors and researchers in this field. And that false belief is that the Fibonacci formula values converge to phi only when using the initial values of 0 and 1. Now, I know I'm losing people already, but please bear with me and we'll go through this and you'll see how this all relates in a minute. Unfortunately, this assumption in the world of mathematics is proven to be false. Formal mathematical proofs, and we'll be going through those and hearing a video on this proof, but they demonstrate that the generalized Fibonacci formulas are in fact the driving force behind this concept of universal Phi convergence, and they work with any set of initial values rather than just the initial values in what's called the Fibonacci sequence of 0 and 1. And it's my contention that this misunderstanding has likely caused those in the field to overlook the generalized Fibonacci formulas as a very simple and elegant model of universal Phi scaling. So what we're going to be doing today in the video, number one, we're going to review the research pointing to the existence of universal Phi scaling. And second, we're going to examine this disconnect between the mathematicians and what I'll call, for lack of a better term, the sacred geometers related to the Fibonacci formulas. Third, we're going to demonstrate the universal Phi scaling properties of the generalized Fibonacci formulas. And finally, we're going to present evidence supporting the idea that these very generalized Fibonacci formulas are the only appropriate mathematical model for universal Phi scaling. So it sounds ambitious. It sounds a little geeky, I'm sure, for non-math majors and non-science majors. But again, hang with me. We'll get through this and you'll be astounded at what I'm going to be showing you today. So first of all, I want to talk about what is universal Phi scaling. I know that that's a question that most of you are not may not be familiar with, and I want to go over that with you now. To begin with, in 2013, Nassim Haramein and Michael Hyson and Elizabeth Rauscher published a paper called Scale Unification, a universal scaling law for organized matter. And in that paper, the authors demonstrate that phi, phi, is found to be a universal scaling constant in nature. And that scaling relationship goes from the cosmological, the galactic, all the way down to subatomic levels, and as far down as what's called the Planck length. So it seems to be universal in nature, and phi seems to be the universal scaling ratio. Here's a picture that comes from a video that we're going to be showing in just a minute to depict this. But essentially what this does is it looks at various elements. You can see the universe down in the bottom right-hand corner, and going up to the top left, it goes all the way up to what's called the Planck length. And all of these various objects that are quantified in terms of their size are conformed to this Phi scaling phenomenon. So an amazing article and proof that phi is everywhere in our universe. Now, similar research has also been done by another researcher named Dan Winter. And these research results are similar. They demonstrate that values of size and periodicity for various physical phenomena ranging from the hydrogen atom to the galactic year. And again, Winter found the very same phenomenon at work, that there was a consistent universal Phi scaling phenomenon at work. Another researcher who has looked into this in a slightly different context is Marshall Lefferts, a colleague of Naseem Haramein. He wrote a book called Cosmometry, Exploring the Holofractal Nature of the Cosmos, just about 2 years ago. And it's a significant finding of Marshall's was an outgrowth of his finding this unique angle in many aspects in nature. And so what he developed, he called the Phi Scaling angle. And you can see that depicted on this slide. Essentially what he did was he took circles whose sizes were based on the Fibonacci numbers and constructed an approximation of a pyramid that would fit inside of those circles whose diameters were increasing by the Fibonacci ratio or series. And this is essentially the depiction of the work that Marshall accomplished. Now, very similar to that, I was looking at the same time, unbeknownst to me, Marshall was doing the same thing, but I was doing this with respect to the Russian pyramids built by Dr. Galit in Russia. And what I was attempting to do was to determine the geometry of these pyramids. And I was able to do that by using the very same phi ratio and a very similar concept of taking successive circles and decreasing their radius by phi, or 1.618. And what I came up with was a pyramid. When I built the pyramid around these stacked circles, that had a slant angle of 76.345 degrees. The only difference between Marshall's research and mine was the fact that he started with the Fibonacci sequence, which is a way to achieve an approximation of phi. I took the actual mathematical equivalent, at least out to 3 significant digits of 1.618, and used that as my methodology. But we came up with essentially identical results, his in 2 dimensions, mine in 3. So you can see that this scaling is everywhere. But what I want to do, Naseem Haramein did an outstanding video, which is on Gaia TV, called Black Hole, where he talks about this in great length. But what I want to do now is to show you a brief 3-minute segment where Naseem explains universal scaling, number 1, but also at the end, he demonstrates the fallacy or the misconception, misunderstanding that seems to pervade in this area of research, namely that the only sequence of numbers that will converge to phi is the Fibonacci series. And we'll talk about that obviously in greater detail later, but I want to play the video for you now.
The universe, with its black hole condition, was the first data point Haramein charted. He next added galactic centers and stars. They lined up in a linear progression with the universe. An amazing result. If the vacuum is the source of the division, then it divides in very specific relationships. The next step was to see if the pattern continued on the other end of the physics scale.
Now we went from stars all the way down to atoms, right across the quantum world, from relativistic equation to the quantum world, and we plotted the energy level of an atom and its radius. And sure enough, the data point lined up again. Now that's a huge jump. And then we went all the way down to the Planck's distance, singularity, and that lined up as well. All the way from universe, which is immense, to a teeny point, billions and billions and billions of times smaller than an atom. And all this, all the data points in between, lining up so very closely to a perfect linear progression. Remarkable. Showing that there is structure, that there is order, that the vacuum is dividing in very specific relationships. And when we start to look at the relationship between the divisions of the data points, we found that the relationships were very close to phi ratios. The phi ratio is found everywhere in nature. When you look at your hand, the end of your finger is 1.618, which is the phi ratio, smaller than the second part of your finger. And the second part is 1.618, smaller than the third part. And your hand relative to your forearm, your arms relative to your body, and so on. Those Fibonacci sequence or phi ratios are found everywhere in nature, in plants, in flowers, the branches of a tree, the roots of a tree, the nervous system of your body, all of the division that produces all of the arteries and the veins of your body, and so on. All phi ratios, all Fibonacci series.
So the key takeaway for the moment is to see from that video with Nassim the literal universality of the Phi scaling ratio. We're going to get back to that last segment where he seems to imply that the only way you can get to phi in any sort of a scaling convergence is by using the Fibonacci sequence. However, we're going to prove that that's not really correct. And we'll be doing that later. But right now, I want to go back to the slides and begin to give you just the basic mathematics of the Fibonacci sequence and explain a few terms to begin with. So let's talk now about the mathematics of Phi convergence. The first thing for those of you who are not mathematicians to understand is what a recursive formula is, because the Fibonacci, the generalized, as I'm calling it, Fibonacci formulas are what's called a recursive formula. So let's find out what that is. A recursive formula is one that repeats or uses its own previous term or terms to calculate subsequent terms and thus forms a sequence of terms. A recursive formula may be an arithmetic sequence, and that means using only addition or subtraction, or it can be a geometric sequence where the terms have either a common factor or a common ratio between them, implying the use of multiplication or division. So let's look at an example of a recursive formula. Actually, the mathematical formula for phi itself is, in all senses of the term, a recursive relationship. So let's look at that chart at the top, and you'll see that what this the definitional formula for phi is the relationship of part A to part B bears the same relationship as the sum of A and B has to A. Now that formula, the proof of this is rather complex, but suffice it to say, we'll see it later actually, but that solution is 1.618 ... This is an infinite irrational number, but that represents phi. And one of the two things to note of importance here, note the recursive or repetitive nature of the relationship. If you notice in the equation down at the bottom, A is to B as A plus B is to A. Essentially, you need to, you're combining two terms in a particular equation to come up with a relationship of a subsequent or larger expression. And that is the definition of a recursive relationship. The other thing that you'll see later on is that this formula is extremely similar to the generalized Fibonacci formulas we're going to talk about later in the video. And so, for example, if you defined A in this formula as 1.618, which is our representation of phi, and you made B the number 1, then the formula for phi shown above is essentially nothing more than the generalized Fibonacci formula that we'll be talking about later, which would have as initial values 1 and 1.618. I know a lot of this is not making sense right now, but just stick with me and we'll get through it. Now to show this in plain common English so that you can understand these formulas a little bit simpler, I'm going to be showing you a number of representations from the sacred geometric literature that demonstrate the fallacy, the misunderstanding that seems to be out in this space regarding the significance of the Fibonacci series and its impact on this process of Phi convergence. So let's read through on the left what this author has to say. For those familiar with the golden ratio phi, you no doubt also familiar with a set of numbers called the Fibonacci sequence. This sequence was first published in 1202 by Leonardo of Pisa, also known as Fibonacci, in his book Liber Abaci. It is derived in a very simple matter. And this is, for those of you who aren't familiar, this is the way it works. If you look at the set of numbers below 0, 1, 1, 2, 3, 5, the line above it shows you exactly how you come up with that Fibonacci sequence. What you do to come up with the third term is to add the first two together. So in that case, 0 plus 1 equals 1. And then to attain the fourth number, you add the second and third numbers together. So that's 1 and 1 equals 2. To achieve the next number, you take the two previous, 1 and 2, and you add the 3. 2 and 3 equals 5. 3 and 5 equals 8, and so forth. So you see how, and that is the derivation of what's called the Fibonacci sequence. And this author goes on to say, this is a sequence of whole numbers that, as it turns out, is directly related to the golden ratio, or phi. When you divide any pair of adjacent numbers in the sequence, the result achieves an increasing accuracy to phi the further out you go in the sequence. And then the author gives these examples. 8 divided by 5, which is the 1, 2, 3, 4, 5, 6th number divided by the 5th equals 1.6. And you go further out to 34 to 55 divided by 34. You get 1.617. 6, then you get further out 1.6179, which is even closer. And then the last number that they use here is 987 divided by 610 equals 1.618032. So what's happening, as you see, the line above those divisions, mathematical phi is equal to 1.61803398887, and it continues forever. It's what's called an infinite irrational number. But you can see that the more the further we go out in that Fibonacci sequence, the more precise the resulting ratio is to the ultimate number of phi itself. So essentially what this is proving is what's called Phi convergence. The further you go out in the series, the closer and closer it gets to the number of phi itself. So that's the concept of Phi convergence, but also this is the demonstration that you're going to see in varying forms throughout this presentation. And what it makes it, what this sounds like to me, and what Nasim's video shows as well, is that there's a presumed relationship that is unique only to the Fibonacci sequence. And what we're going to be proving is that that's not the case. So to read again the commentary there on the right of the page, this example and the ones that follow are examples of numerous discussions of Phi convergence using the Fibonacci sequence. The focus on the Fibonacci sequence is the only set of initial numbers producing Phi convergence is misleading. The generalized Fibonacci formulas alone are sufficient to provide these results, and Phi convergence, in fact, has nothing to do with any special properties inherent in the Fibonacci sequence. So this is a first example. I'm going to show you several more just so you can see that this is fairly pervasive. It's not universal, but it's very pervasive in the literature. Here's another individual who is coming up with the same basic results. You'll see that they are doing the same kind of an analysis at the bottom of the page there. showing the successive convergence to phi that comes from the formulas associated with Phi convergence, but they are using the Fibonacci sequence. Here's another one. This is actually from a book that I own that's not available in PDF format, or at least I couldn't find it. And so I took a picture of this out of that textbook. You can see the same kind of derivation, again, using the Fibonacci sequence. Here's another one from the internet doing the same approach of convergence to phi based on the Fibonacci sequence. And here's another one, again, from the internet, using the same basic methodology. So, and lastly, here's one with a title which is as clear, quite honestly, a misrepresentation as I found. Leonardo Fibonacci discovered the sequence which converges on phi, which we will find out in a few moments is not true. Here's a depiction in graphic form of the convergence of phi in graphical format. And this is helpful because whether it's being done with the Fibonacci series or with any other two numbers that use these same generalized Fibonacci formulas, you're going to end up with something that looks very much the same as this chart. In this example, we start with the first ratio at the top left-hand corner of 2 divided by 1, and we get a result of 2. The next set of numbers is 3 divided by 2, and that ends up being a ratio of 1.5. Then we divide 5 by 3, we get a ratio of 1.6. 6, 7, then we get a ratio of 1.6 with 8 divided by 5 and so forth. You can see that what happens with each successive ratio, we're trending or converging more precisely on the phi number of 1.61803398887 and continuing. So again, the information on the right there. In this depiction, the reader is once again lulled into believing that the Fibonacci sequence is the only way to achieve phi convergence. And this erroneous inference hides the fact that phi convergence is a result of the formulas themselves and not to the Fibonacci sequence. So to leave the erroneous and or misleading examples in the past, I'm going to start to show you some of the few that I have found that at least mention this correctly, one of which is an internet site called cosmiccore.org that's done by Renee Hoadley. I have recommended this site in the past for those of you who are interested in the Platonic solids and sacred geometry. This is an outstanding source for information on these topics. But she's done the same kind of phi convergence chart in her explanation. But I want you to look down in the bottom little section there, the last 2 lines where she does say you can actually select any 2 numbers, not just 0 and 1, and adding each consecutive pair to the next term, and the ideal limit will always approach phi. So here's somebody who's beginning to get it right, and was one of the people who helped me to originally think up the idea of testing this on my own, which is the way I found this 4 or 5 months ago. Knew that this was out there, and I knew I needed to get a video out on this to clarify it. So my congrats to Renee, and my thanks for leading me one of the very few places in the right direction. Another book that I have in my possession that has this information right as well, and in fact goes into even greater detail in terms of explanation, is Michael Schneider's book, Fibonacci Numbers and the Golden Mean. And again, I have a hard copy, so I had to take this with my phone as a photograph, so it's not very pretty. But I want to read the two paragraphs because there's lots of important information in these two paragraphs. The ratios of low Fibonacci numbers begin wildly high, similar to what we were talking about or demonstrating in that previous graph, but quickly zoom toward their ideal relationship. This is called by mathematicians an asymptote, something approached but never actually reached. And while we call it a number, we're actually looking at a relationship, a key point that we're going to bring up later in the video. This value 1.618 ... has been symbolized by the Greek letter phi, named after the Greek sculptor and designer of the Parthenon, Phidias, who used it in his works. It is also called by other names, including the golden mean, golden ratio, and golden section. An important topic here in the second paragraph. While this relationship of Fibonacci numbers is associated with phi, don't be fooled by appearances. It's not the Fibonacci numbers themselves which make this possible. It's their accumulative process which funnels their ratios towards phi. And what he means by accumulative process, I'm defining as the generalized Fibonacci formulas. So he's saying exactly the same thing that I discovered independently and only realized when I went back to do this video that he had mentioned this earlier, or I had seen this earlier in his book. So now for the ultimate proof, I'm going to play a video for you now from Numberphile, which demonstrates, and they call it the golden proof, but it demonstrates that the generalized Fibonacci formulas are the drivers of Phi convergence. So this video is going to set it straight once and for all. The Fibonacci series initial numbers of 0 and 1 are only one of an infinite number of initial number pairs that will produce Phi convergence. So if you'll bear with me, I'm going to start that video now, and we'll be back in a moment.
Fibonacci numbers again, start 1, 1, 2, 3, 5. And the rule is, if each number here equals the ones before it. So if this was the nth number, and we're going to call that xn for the nth number, it equals the one before it plus the one before that. So it equals xn minus 1 plus xn minus 2. So that's our defining thing. And what we're trying to find ultimately is what is the ratio between two of the numbers. But importantly, because we're looking for the ratio and is approaching in the limit, it doesn't matter which two terms. It should be the same ratio, give or take. And you know, if you do it for infinitely many, the same ratio for all of them, but for any two of the terms. So what we can say now is the ratio between x to the n and the one before that, which was x to the n minus 1, one before, should equal the same as the ratio between xn minus 1 to the one before that, which was xn minus 2. And we're going to call it, what letter would you like, Brady, for any Greek letter? Do you have a favorite?
Delta?
Delta. Okay, so let's do a capital delta because it's quicker to draw. So we're trying to work out this ratio delta is, and we know it's the ratio between any two consecutive terms. Now we know, according to our relationship which generates the sequence, that xn equals the two before it added together. So I'm going to put that in instead of x. So all I've done is substitute that in. But now I can start simplifying because I've got the same term there twice. So in fact, if I divide through, that's 1 plus x to the n minus 2 over x to the n minus 1, which still equals x to the n minus 1 over x to the n minus 2, which still equals the ratio delta we're looking for. So now you will go, hang on a second, that is the same as this, but upside down. And in fact, that equals that ratio delta. So I can now change this to be 1 plus, well, that's the inverse of this ratio. So that's 1 over delta equals, and that there is the delta. And so the relationship for the ratio of any sequence where you get the next term from adding the two previous ones, 1 plus the inverse of that ratio equals the ratio. Now, what ratio could that possibly be? Well, let's work it out, because we can turn this into a quadratic. If I multiply through by triangle, it equals that plus 1 equals triangle squared. And so delta squared minus delta minus 1 equals 0. So all I've done is rearrange that formula. Now we can solve this using our friend the quadratic equation, because we know that if you have a times x squared plus phi x plus c equals 0, then x equals negative b plus or minus the square root of b squared minus 4ac over 2a. So we can substitute in to use the quadratic formula. So we now know delta equals negative b, which is the coefficient there, which will be 1, plus or minus the square root of b squared is going to be 1 minus 4 times 1 times negative 1. So it's going to be plus 4. 2 times 1 is 2. So that's going to equal, now I'm only going to use the positive for now, 1 plus root 5 divided by 2, which is the golden ratio. If you actually work that out, that's where 1.6180 blah comes from. And in fact, that's one of the definitions of the golden ratio. And so that's why for any starting terms, it always approaches that same sequence. If you use the negative, you get the negative inverse of the golden ratio. Another wonderful property of it. If I'd use the negative, if I'd used equals 1 minus root 5 over 2, then that equals negative 0.6180 blah. So they're the two solutions for that particular equation. So that's why it works for any sequence where you add two terms to get the next one.
So the Fibonacci numbers meant nothing.
The Fibonacci numbers are one of an infinite family of such numbers, because for any two whole numbers you want to start with, the exact same thing works out. In fact, why use whole numbers? Go bananas. At no point did I specify whole numbers here. It just, whatever you start with, add two terms, you get the next one. You always get the golden ratio. That's not some special property Fibonacci numbers have. All of them have got that property.
Well, for those of you who made it through the 5 minutes of that video, I hope you're convinced now that for some reason, the world of mathematics and the world of sacred geometry just have not been in sync on this topic. And I think it's, as I'll say again later, I think this has been a major factor in the inability of the community to come up with a methodology to come up with a formula, scaling formula, for this universal Phi scaling phenomenon. But with that said, we're gonna continue on, because I want to show you the results that I've achieved. First, I want to just show you, though, how small a difference it is to take this traditional mathematical derivation of phi and convert it into a universal one, because all it is changing the definition of the first two numbers in these equations. But I'll go through them in math speak so that you guys can understand what's going on. We're going to define f as a Fibonacci number. F sub n will be a number 3, number 4, number 8, whatever it may be in the series of Fibonacci numbers. And R is defined as a Fibonacci ratio. So let's go through these equations, and first I'll define them in math speak and then in plain English. First of all, f sub n is equal to f sub n minus 2 plus f n minus 1. Now, what does that mean in English? If we define fn as the third number in that series, you know that 0 and 1 are the first two. Well, f sub 3 would be the third number, and that could be 1, and it's equal to fn minus 2, which would be the first number, or 0, plus the one previous to it, which is 1. So it's just a way of formalizing that relationship on what's called a recursive basis that we're going to add together for any particular term, the two previous, to come up with the next Fibonacci number in the sequence. And then R sub n, which is the Fibonacci ratio, is nothing more than taking the third Fibonacci number and dividing it by the one before it, or fn minus 2, minus 1. So if fn is the third number, you divide the third Fibonacci number in the sequence by the second Fibonacci number, and you'd come up with the ratio. So that's the definition of this in mathematics. with the only exception, when you define this only in terms of the Fibonacci sequence, you are making a special case where F1, which is the first Fibonacci number, is equal to 0, and the second Fibonacci number is equal to 1. But defining those as 0 and 1 is really just taking a special case of taking these general Fibonacci formulas and defining them as a special case of F1 equals 0 and F2 equals 1. All right. Now, all that we do to convert that to the generalized Fibonacci formulas and use that as a recursive universal Phi scaling formula is to change the definitions of F1 and F2. And instead of defining them as 1 and 0, all we've done is we'll state that they can be any two numbers other than 0 and 0, because obviously you can't, if you add 0 and 0 together, you're still going to have 0 and the whole thing won't work. But with that exception, any other set of numbers or less than whole numbers will also work. So that's the only difference that we have to make. Very simple once you understand the universality of the Fibonacci formulas to achieve the Phi scaling relationship. So now I'm going to show you some research, show these in spreadsheet form so you can watch these and see for yourself how this all works out. This is a summary of some spreadsheets I put together. This was the research that got me to my understanding. And so to summarize, again, we're going to see that it's not necessary to use the Fibonacci sequence to achieve Phi convergence. The speed with which these sequences converge to Phi is remarkably consistent no matter what the initial values happen to be. Any two beginning numbers will achieve Phi convergence, again, so long as the beginning numbers, both beginning numbers are not 0. And the sequences can be scaled in reverse with perfect precision. And this is an important topic as that we'll discuss later in greater detail, but we have to be able to not only scale up, but also to be able to scale down with the same exact precision. So let's begin looking at these numbers. I've color-coded these. I have 5 examples that I've put together of these series, and that's to help us to visualize them. We start on the left, we have the actual Fibonacci sequence itself, and we'll use that as an example or a template to show how the spreadsheet is set up. You'll see here the first number is 0 at the top, and the second number is 1. We're going to have the first and second number at the top, so they're easy to see in each of these cases going forward. Now, as you go down to the column on the left, you'll see that first and second numbers, 0 and 1, are in the column. And again, you're going to see that we're using that Fibonacci formula of adding the two previous numbers together to achieve the next number in the sequence. So we start off with 0, 1, 1, 2, 3, 5, 8, 13, 21, and so forth. And in the next column, you see the associated ratio between the current Fibonacci number in the sequence and the one previous. So in this case, again, the standard Fibonacci sequence relationships, you start with, depending on whether you start with 0 and 1 or 1 and 2, you start with 1, 2, 1.5. You've already, in this case, you see, hit an irrational repeating fraction by the fourth iteration, and you have 1.6 and so forth. An interesting thing to note is that after the ratio of 13 to 8, every single number past that point is an infinite irrational number. But anyway, you can see that the scaling relationship is there. It rapidly approaches Phi, and by the 24th iteration, in fact, that I used that on purpose. I picked 24 iterations because that was the point at which every single one of these examples ended up coming out to the phi approximation to 8 significant digits. So in this case, that is 1.6180339. Could have continued it on further, as we've seen from the videos, and gotten even more precision, but that's where I stopped. Now to show you the examples that prove the universality of this Phi convergence formula. The first number in the second example is 10, and the second number is 4. So they're not even going in increasing numbers, but yet the same formula will work. And you'll see that we put 10 and 4 in here, and sure enough, it converges to phi, just like the Fibonacci sequence does. Again, disproving immediately the fact that this is that the Fibonacci sequence is unique in having any properties that affect phi convergence. The next set of numbers, I started with 1, and the second number is 1,000,000, just or billion, excuse me. So I just wanted to see if that would make any difference, primarily to see if it would converge basically as quickly as the other numbers. And sure enough, by the 24th iteration, it as well was precise to 8 significant digits. So these 3 examples, I've called this page Phi convergence with positive numbers for a reason. Each one of these numbers was a positive number that we started with, both in the first and second numbers. But on the next page, I've gone ahead and just to show you what happens if you use, for example, in the first case, a positive number to begin with, and then a negative number as the second number. Well, it really doesn't seem to make much difference, because when we do that, we once again very rapidly, using the generalized Fibonacci formulas, we achieve a Phi scaling down to 8 significant digits within 24 iterations. And similarly, if we take make the first 2 numbers negative, -5 and -10, we get exactly the same result. The only difference in this case is that by starting with 2 negative numbers, we end up with a negative number as an ongoing result. But still, the Phi scaling is achieved, is exactly the same, and achieves the Phi to 8 significant digits within 24 iterations. So, so far as we can see, it doesn't matter at all. This is just visual proof of what the folks from Numberphile explained in the video. Every single combination is going to converge on phi. But now let's try this in reverse. The ratios that we generated in the previous spreadsheets all demonstrated phi convergence, and that was even though some of the series contained negative and or positive numbers, and some series were getting larger and some were smaller. So we got a lot of diversity in those 5 examples. But what happens when we reverse the process? Will we be able to precisely replicate the original results? And the answer is yes. So what this is going to demonstrate is that the generalized Fibonacci formulas will scale both upward and downward with perfect precision. So we're going to look now again, as for starters, at the Fibonacci sequence. We started with 0 and 1. Again, we took it out 24 iterations in the first 2 columns, as we'd seen before. Now, what I've done, I've taken those same 2 numbers, last 2 numbers, 46, 368. I've made that the first number in the reverse series, and 28, 657 as the second number in the series. And I've reversed the process. Now, the equation has changed a little bit, because rather than adding to the numbers, we're going to be subtracting numbers, and also the ratio is going to be changed as well to maintain the phi relationships. We're going to be looking at the relationship between the previous. We're going to start with the previous number and divide it by the current number rather than the other way around in order to achieve that unity. But if you look at these pages, you'll see that you end up with 0 and 1 as your first and last numbers. And if you look at the relationships of the ratios, they are the mirror image. Nothing has changed whatsoever in the ratios going in the left column from top to bottom. And then the mirror image of those is in the right column going from the bottom to the top. So everything is a perfect mirror image of the in the declining sequence as it is in the ascending. The same thing is going to hold no matter what scenario we look at here. We have, in this case, 10 and 4. You'll see that 4 and 10 show up in the bottom right-hand corner. The sequence has been reproduced, as have the ratios, with perfect precision. And we'll get into why that's the case here in a few minutes. But I just wanted to prove to you that it doesn't matter which of these 5 scenarios we start with here, 1 in a million. That gets us up to actually 46 trillion as the last number, and 28 trillion as the next to the last number. You can do exactly the same thing. It makes no difference whatsoever how big or small the numbers are. And here again, with the same set of, we have a positive and negative number. We achieve that exact precision and the mirror images on the ratios. And here again, the last example, -5 and -10 proves out as well. Now that's important because this demonstrates that the generalized Fibonacci formulas allow, as I mentioned before, for perfect scaling both upwards and downwards. And it's universal in nature. So every single number combination that we can come up with will abide by this formula. So now that is an amazing and an astonishing result, given the fact that, as we saw, most of the people who work in this field seem to think that the Fibonacci sequence had some unique property which allowed this to occur for only one unique set of numbers. Again, to repeat, every single number combination that we can come up with will scale uniformly to phi based upon these generalized Fibonacci formulas, and thereby meet a definition of a universal scaling formula for phi. So I want to talk now that we know that it meets these definitions, I want to talk about the practical limitations of actually finding an alternative universal phi scaling formula, because this is equally as important. Neither phi nor any irrational number can be used as part of a recursive scaling formula due to the simple fact that an infinite irrational number such as phi cannot be precisely replicated over an infinite number of iterations without rapidly losing precision. Now, why is that important? We're going to talk about fractals in a moment, but all of you who have seen fractals, you know that those beautiful patterns, they replicate precisely from layer to layer to layer. And the only way that that can occur is if there is a perfect fractal correspondence in the scaling from one level to the next. And if you use any irrational number, including phi, in a scaling relationship, that's just not going to hold up because what's going to happen is that very quickly you're going to lose your precision, and those beautiful fractals that we're used to seeing would become blurs and blobs. So it's not going to work. The other thing to remember that we learned from Michael Schneider's page earlier on, phi is not even a real number. We use an approximation of phi in calculations, but it is not a number, but rather a relationship, and therefore another reason why phi itself can't be used as a part of the scaling function. The second thing to know is that the only way to guarantee infinite precision in any kind of a scaling formula is to use a scaling function that is purely arithmetic in nature, i.e., only addition and subtraction. And as you notice, that's what we were doing in our examples, and that's what the people from Number Phi told you was necessary as well. So using only addition and subtraction is key. Even though multiplication of numbers can produce other numbers, especially whole numbers, multiplication will produce other whole numbers, the same is not true for the process of division. And we saw that already. If you divide even numbers such as 5 divided by 3, you end up with an infinite repeating fraction, which cannot be scaled in precision over an infinite number of iterations. So attempting to develop a universal scaling formula based on a geometric recursive formula, which again means one using multiplication and division, would be incredibly complex, far beyond my ability to comprehend, and would violate the principle of Occam's razor in any event. And that states that you always want to, when you have a bunch of options, which in this case, we have not found another option, but if we did, we'd want to use the simplest of competing theories as the preferred option to consider. So given all of these practical limitations and the fact that there's no other formula that's been put out there to define a universal scaling formula with phi, it appears that the generalized Fibonacci formula appears to be the very best, and at least currently is the only available model that I know of for universal phi scaling. So I think this is an important thing to bring to everyone's attention. I think it's been perhaps overlooked again because of this misunderstanding for whatever reason that has occurred within the sacred geometric community. A lack of communication, obviously, between the mathematics world and the sacred geometry world that you wouldn't necessarily expect. The final thing I want to talk about before we finish up today is that the generalized Fibonacci formulas produce what I'll call fractalized sets. And let me explain what I'm saying by that. Again, any two numbers within the set, once we've established the original two numbers, you can take any two numbers in that particular set, and you are able to derive all of the rest of the numbers in that set from beginning to infinity just by virtue of using the Fibonacci formulas. And so as an example, I just picked out 610 and 377. This is from the Fibonacci series, but it would work with any set of these numbers. You can scale upward or downward to infinity or to the beginning and get those exact results. So in essence, all you need are two numbers from a set that's based upon two initial numbers, and you can determine everything there is to know about the entire series. And in effect, it's like having the fractal equivalence at your fingertips without having to do any derivation equations. So very powerful. So anyway, the next steps in this is brand new, and there's a lot more work to do to prove out this model. I've already discovered a number of interesting relationships that I don't want to go into today. It would muddy the waters a little bit, and I want to have time to search those out and refine them. But I'm going to be doing some subsequent videos about this. But clearly, the next steps in verifying this model, in my view, is going to be to attempt to see if there's ways to integrate this scaling model with vortex mathematics and the torus. And just to show you what I'm talking about here, this depiction on the left, this is a torus. It's a picture that I put together showing the tip of the pyramid inside as the midpoint of the torus donut hole. This is the geometry that seems to correspond to this phi, it does correspond to this phi scaling. So what I'm expecting or I'm hoping to find is that we can take this scaling formula and apply it to the torus using vortex mathematics, as has already been done by other researchers and depicted in the picture on the right. So that's where I think this is going to go. I'm really excited about this. This is something, this has been a missing link that I think has been missing for a long time. And at least now we have a model that others can look at as well. And in my final bullet point here, I welcome any and all comments and assistance in pursuing this as the universal phi scaling formula for the creative process. So if you'd like to, if you have comments, questions, please feel free to contact me at the phone number and email listed below. So I thank you for watching today's video. This is one of a number of videos that the Pyramid Science Foundation, has done for the benefit of mankind. We work off of donations and support. You can support us by buying our pyramids and accessories through Lisa Richards at Pyramid Surge as well. But if you'd like to give donations to help see this kind of pyramid research going forward, we would appreciate it if you go to pyramidsciencefoundation.org and make a tax-deductible contribution. I thank you for watching, and you have a great day.